Okay, the timer 555 pinout is this. It's an 8-pin integrated circuit, and these are the pins, and these are the internal workings. And there's important pins here that I will mention. Worth to mention right now is first the output. This is the output signal generated by the timer. Then the trigger. The trigger sets the output to high when its input is less than 1/3. When the input here is less than 1/3 of the VCC voltage, then the output is turned high. I will not use a reset, and I will not use a control voltage. And the threshold sets the output to low when the input is higher than 2/3 of the voltage. When the input to this pin is higher than 2/3 of the voltage here. Pin 7 is set to ground when the input to pin 6 reaches 2/3 of the value of VCC, and while pin 2 is higher than 1/3 of VCC. So pin 2 has preponderance over pin 6. So how can you generate a pulse width modulation signal coming out of this IC? So here we have the connection. So here I have, as I showed you before, the part where I have the motor and the flyback diode and the test LED and the noise filtering capacitor. And this, I use this small BJT transistor. So what happens here is this: I have this capacitor, which I use in the circuit. As soon as I turn on this circuit, this capacitor will start charging, but initially it will be at less than 1/3 of the value of VCC. So the trigger will set the output on. The capacitor will continue charging until the threshold reaches, pin 6 reaches 2/3 of the value of VCC. At that point, the output will turn off and the discharge will be set to ground. If this is set to ground, then the capacitor will start discharging through this path. Will start discharging through this path. So you will have and it will take some time to discharge, and at one point the value of the voltage here now will be less than 1/3, and the cycle will repeat. So the capacitor charges through this path, and at one point it will set the threshold. The threshold will set the discharge to low, and at that point the capacitor will discharge through this path, and it will start discharging until it reaches until the trigger reaches a value of 1/3 of the voltage here in VCC, and at that point the output will go high, and the discharge will go also to high, and in that way the cycle will repeat. So here I'm showing the signal, and this is the signals to the trigger, both the trigger and the threshold, and you can see that it starts because of the charge of the capacitor, it starts charging. At one point it'll start discharging, and it'll start charging and discharging, and the discharge signal is here, and the output is shown here. You see that you have on, off, and the values of the resets and the values of the control voltage are set here to fixed value during the entire cycle. Okay, the formulas to obtain to know how much the frequency will be in this circuit, you set the potentiometer, you set it to an x fraction of the potentiometer maximum value, and then you use C1, and then the T on value will be this one. For example, in this circuit, if you set x to 0.5, you set the potentiometer in the middle, then you will have 0.5, the value of x. Then RP used in our circuit is 2 kilo ohm, and C1 we're using 0.2 microfarad capacitor. The T off is governed by this equation, as you can able to verify in the circuit. And the pulse width modulation period, T, is T on plus T off. So when I set the potentiometer at x equals 0.5 in the middle of the range, then I'll get a duty cycle of 33%. And one of the problems that the 555 circuit has is that it cannot cover the entire range of duty cycle. Here's the circuit. You can see here the potentiometer, the two diodes, resistance R1, capacitor C2. Here's the 555 timer, and here's pin 3, the output. Here are the base resistance, and this is the flyby diode, and this is the LED which dims according to the pulse width modulation cycle, and this is the resistance in series with the LED. And here we have the power transistor. Okay, here's the experimental setup. Here's the tachometer. Here's an oscilloscope where you can see the pulse width modulation signal. Here I have a power supply, the gear motor, with the DC motor with the gearbox and the reed switch, magnetic switch, and here's the circuit. Okay, here I show the results that I obtained. When I I measure the pulse width modulation. I measure it with the oscilloscope, and the RPM with the tachometer based on an Arduino, and this is the curve that I obtain with this the 555 a maximum of around 95% of duty cycle down to around 35%. Below this, I cannot reach a value below it, and also the motor stops, or I cannot get a pulse width modulation duty cycle lower than this. And also you can see, it's interesting that it's not a linear curve. It's a quadratic curve, and this is the equation that describes this quadratic curve. Okay, thank you very much, and I hope it has been useful for you.